Hi, my name is Niclas, and for explaining my PhD topic I will talk about extreme precipitation, the global oceans and mathematics. So nowadays weather forecasts are quite accurate when we're talking about the next few days. However, it's a completely different story when it comes to predicting the weather some weeks or even months in advance. In particular, the amount of precipitation is quite difficult to forecast. At the same time, extreme precipitation can have huge impacts. For example, in the EU, the cost of damages caused by extreme precipitation over the last 40 years amount to about €500 billion. That's more than what the EU spends per year on education. Obviously, the more time our society has to prepare for such events, the less will be the economic and human costs. Imagine you would know weeks or even months in advance that such an event will occur. What I'm trying in my PhD is to improve exactly these forecasts. So how can you do this? One way is to look at the ultimate moisture source on Earth, the oceans. There are basically two reasons for that. First, the hydrological cycle. This is the cycle that you probably all studied in school and which tells you in a simplified way that water which evaporates over the ocean and precipitates as rain on the continents eventually comes back to the ocean, describing a full cycle. That means the more water evaporates over the ocean, the more rain tends to fall on the continents. A second reason for looking at the oceans is the role in the energy distribution around the world. A good example for this comes from the Pacific Ocean, where cycles of enhanced and reduced heat release from the sea surface are known as the El Niño Southern Oscillation, or short ENSO. These ENSO-related energy fluxes can bring extreme precipitations or droughts all over the world. But are there other ocean-related processes like ENSO that could drive precipitations? In order to investigate this, we looked at time series of over 60 years of sea surface temperature and precipitation to see if they behave similarly. Unfortunately, there are a couple of things that make this approach complicated. First, we have not only one time series, but actually thousands of time series. Secondly, each time series is a complex mixture of different processes: the seasonal cycle, ENSO, global warming, so in short, the whole messy climate system. And thirdly, we're looking for precipitation changes that occur after changes in sea surface temperature. Of course, because we want to predict precipitation. But how do we find the time shifts which can be different for each time series and each process? So luckily here, mathematics is our friend. So using some clever mathematical tricks, we can actually tackle all of these issues. By applying something which is called dimensionality reduction, we can look at only the most interesting time series and separate different climatic processes at the same time. And by making our time series a little bit more complex, we sometimes can even identify time lags for different time series. But no worries. If you haven't understood everything, we have submitted a paper which is currently under review, but you can check the preprint already now. I guess the link will be here somewhere. Will the link be here? I hope so. So thanks for watching and see you soon. Ciao.